Everybody, I wanted to take a little bit of time and go over a stoichiometry problem, kind of soup to nuts here for problem number 6. And so let's get started. In order to do this question, we need to start with writing a chemical equation. Now, we're not going to necessarily worry about balanced yet, or are we going to worry about including states, but we need to be able to write the formulas of this compound. And so nickel is Ni, and then that means that it's nickel 2 plus. And then phosphide, remember if it ends in IDE, it's just the element, and then that's 3 minus. And what is the least common multiple between 2 and 3 is 6. So this is going to be 3, and then this is going to be 2. So nickel phosphide is NiP. So, or Ni3P2. Okay, so let's put that here, Ni3P2, and that's going to react to form. And now this is a decomposition reaction, so typically we wouldn't necessarily know what a decomposition reaction forms, except we're given in this one that it breaks down into its elements. So we know that nickel is found as Ni, and then we also know that phosphorus is found as P. Okay, these aren't the diatomic elements. They're not Haeckelbrief, so we don't have to worry about those. Okay, and so now we can include the states. Okay, and the periodic table can help us. Anything over here, these guys are gases. Bromine and mercury are liquids, and the rest are metals. Okay. A lot of periodic tables are color-coded. So this guy here is a solid. Okay. Nickel is a metal, so most metals are solids. And this guy, how do we know what nickel 2 phosphide is? Well, it's an ionic compound. And for the purposes of just life, we will assume that almost every ionic compound, we will assume that all ionic compounds are solids. Okay, there are actually some ionic liquids, and I did some research on those, but anyways, we're going to assume ionic compounds are solids for the most part. So now we've included the states, and we've made a chemical equation, so now we just have to balance this guy. I'm going to balance it in blue, and so notice we have 3 nickels, so I'm going to put a 3 here. We have 2 phosphoruses, so I'm going to put a 2 there. And so that is pretty straightforward balancing. So that makes us done with part A. And then part B says we have to predict how much, or calculate how much, determine how much is in moles. And then part C is convert those moles into grams. So what we're trying to do is we're trying to use an ICE chart to come up with this box and this box right here, because this is the initial change, and how much initially we have will be related to how much at the end we have. So we can use this value to get this. So let's make sure that we have that written down. I'm going to put it in a separate color just to make sure that we, okay, just so it's separate from the periodic, or from the ICE chart. Also keep in mind that any number that's in the ICE chart is typically going to be moles, not grams. Okay, so now we have to convert to moles here. Anytime we do chemistry on paper, the math of chemistry on paper is usually done in moles in order to do a bunch of it. So we're going to convert this to moles. Okay, so we're going to go 53.73 grams of Ni3P2. We're going to X-line it, and now we're going to convert grams to moles. How do we convert grams to moles? Well, we need the molar mass. So before we actually do this math, we're going to have to come down here, and we have to look up nickel, which is 3 times some value. We're going to have to look up phosphorus, 2 times some value, on the periodic table. So nickel's right here, and that says 58.693, and phosphorus is 30.974. Okay, so let's make sure that we get that. Okay, so this is nickel is 58.693 and phosphorus is 30.974. Do the math. So it's 3 times 58.693 times 2. Oh, helps if my calculator's on. Okay, clear out this junk. Okay, so 3 times 58.693 plus 2 times 30.974, and we get an answer of 238.027. That's grams per mole. Now, you let the units tell you how to do this. So this is 1 mole, because it's grams for every 1 mole. And this is 238.027. Okay, on the bottom. So we're going to do math now. So we're going to finish this. We're going to go 53.73 times 1 divided by... Now, if you don't want to include the 1, that's fine. But I'm just kind of doing what it says here. Divided by 238.027. And we get 0.2257 moles of Ni3P. Now, notice 4 significant figures because we started with 4 significant figures here. Okay, so this is going to be 0.2257. Okay, and I'm not going to put units in there because it's assumed that units on the ICE chart are moles. Okay, so once we get this, now we can fill in a couple of the other boxes on the ICE chart. Okay, first of all, I'm going to put 0 and 0 here because it doesn't say that we started with any nickel or any phosphorus in the problem. So we can say 0, 0 here, and that's true anytime. Doesn't mention it in the problem, we're going to assume that it's 0. The other thing that we're going to do is we're going to assume, which is a reasonable assumption, that this is going to react until it's all gone. There's nothing else that it's reacting with. So the reaction is going to stop when we've used up all the nickel to phosphide. So this is going to, at the end, there's going to be 0 of this. So that means that this is going to change by... we're going to have to subtract 0.2257 moles. Now, I can't emphasize enough that as soon as you kind of get this, this is going to get us this, and then figure it out. This is like the most important thing, that first change box. Okay? In order to calculate how much nickel is made, we're going to figure out how much nickel 2 phosphide is used, and that's how much is used. So we're going to go from here to here, and from here to the same thing with phosphorus. When we're going across the period, the ICE chart, when we're going from moles of something to moles of something else, we have to use the balanced chemical equation, or the ratio, or the coefficients, or whatever, however you want to say that. We're using those values. Okay, so I'm going to put a little line here because I'm going to indicate that we're doing kind of a new step in the problem. Okay, and so what I know is that I have 0.2257 moles of Ni3P2. We're going to X-line it because that's how we convert all our values. And now instead of worrying about mole or gram, we're trying to get rid of Ni3P2, and we're trying to convert that to nickel. And we're going to use the coefficients of our balanced chemical equation, and we know that for every 3 nickels that we produce, we need 1 nickel to phosphide. So this is in a ratio of 3 to 1. Okay? And so now we do the math. We do 0.2257 times 3. I'm not going to actually divide by 1 because that's going to give us the same answer. So it's 0.6771. And the units on that, look, that cancels to give us moles of nickel. Okay, nickel, great. So we're going to take that and we're going to put it here. So we're going to add that because for every one of these that's used up, 3 of these is added, so it's 0.6771. We do a similar calculation to figure out how many moles of phosphide we're going to use. We start with the moles of nickel 2 phosphide. Whoops, 2. And then we're going to get rid of nickel 2 phosphide, and we are going to convert that to phosphorus. So it's going to be, for every one of these, we have 2 of those. That's the coefficients, the balanced chemical equation. So again, if we look at what units we're left with moles and moles of phosphorus. So you may be able to do this in your head. You don't have to necessarily plug it into the calculator if you don't need to, but I'm going to do it because it's because it could be that you can't do it in your head, and that's fine. So it's 0.2257 times 2. Okay, and actually, I probably wouldn't be able to do this in my head. I kind of misread that number in my own head. So, okay, anyways, but that's the number, and it's in moles of phosphorus. So now we're going to go up here, and we're going to go 0.4514 moles of phosphorus, and because we're making it, we're going to add it. So this is 0 plus that, 6771, 0 plus that, 0.4514, and so now we've in essence answered part B. We need to do part C here because we want to convert to grams. Well, how do we convert to grams? We use the molar mass. We're going down here. We're going to put an answer below here. And so we're going to use the molar mass of nickel and of phosphorus to convert. So again, I'm going to put a little line here. I'm going to do the math, and I'm going to convert 0.6771 moles of nickel, and now I'm going to X line it. I'm going to go from moles on the bottom to grams, and I know that I have 1 mole. Notice I'm not trying to go to the periodic table because I know that I wrote it down somewhere and I've labeled it well, so I'm always kind of labeling and doing things in an order so that I can go back and refer to these things. So it's 58.693 here, so this is 58.693, and so now 0.6771 times 58.693, and that's going to equal 39.74 grams, because moles cancel, of nickel. Okay, so I'm going to go up here. I'm going to do this in a different color just because I don't want to get confused with all my mole calculations. So this is 39.74 grams. Okay, I'm going to put grams, the units there, because I don't want to, again, get confused. Okay, now the second one is moles of phosphorus. So it's 0.4514 moles of phosphorus. We're going to X line this guy. Again, moles on the top, or on the bottom, grams on the top, and we're going to use the molar mass of phosphorus, which we have is 30.974. So for every 1 mole, we have 30.974 grams. Moles cancel, and we're left with grams of phosphorus. So we do 0.4514 times 30.974, and we get an answer of 13.98 grams of phosphorus. So I'm going to go up here. I'm going to go, again, a little different color. Too far. So this is 13.98 grams. So that answers part C, but I did all this work. Here I have like 14 minutes in. I want to make sure that I got the right answer. So I'm going to use the law of conservation of mass to help us out. So over here, I'm going to draw a line, and what I know is that the law of conservation of mass says that however much mass we have at the beginning in all this stuff, should equal all the stuff we have at the end. So 53.73 grams plus 0 plus 0, so that's 53.73, should equal what we have down here below. So that's 39.74 plus 13.98, and we get 53.72. And that is close enough because, you know, we've rounded numbers and we've used significant figures, and we used not wrong values in the periodic table, but, you know, we've had different values in the periodic table that may be slightly different. So yeah, there it is. And I would say that that checks, because it's going to be very rare that if you screw something up that these numbers are just going to accidentally equal each other. There's too many places for errors to occur. So that's your answer to problem number 6.